I am Seok Jang from Queen's College and also the Graduate Center of the City University of New York. And Chris Baldwin and I have been organizing these workshops through this Initiative for Theoretical Sciences at the Graduate Center. This is already our fourth workshop. So we have high profile, exciting speakers today who all are going to talk about multi-exciton processes, spectroscopy and dynamics of multi-exciton processes. Each speaker will be given 30 minutes and 20 minutes will be uninterrupted talks. During that time, if you have any question, you can submit your question to either Chris Baldwin or to all the participants. I'm happy to introduce our first speaker, Carlos Silva from Georgia Tech. Carlos, it's your turn. You can share your screen.
So thank you very much, Sagi, for the introduction and also for the opportunity to speak. I'm very happy to be part of this workshop. So you can see my screen right now. I'm very happy to be part of this workshop. I'm very excited about this work that is unpublished work. Pretty much everything that I'm going to be talking about right now is unpublished in collaboration with Eric Bittner, who is the next speaker and will present the continuation of this work. Basically, the theoretical aspects. It concerns Frenkel Biexcitons in organic semiconductors, particularly in polymers. And so why are Frenkel Biexcitons something that we don't hear about too often? So we will discuss that in the course of the next two talks. But what I want to do is first show you our evidence or our spectroscopic measurement of spectral Biexciton resonances and a means, using that as a means to quantify binding energies as well as the nature of binding. So that's what the subject of this talk is about. Let me just start out by acknowledging the people who have done this work. So at Georgia Tech, this is mainly the PhD thesis work of Elizabeth Gutierrez Mesa, a PhD student who is going to finish in the next few months her thesis, and this is one of the key chapters of her thesis. And Raven Malatesta is a second-year PhD student who was pretty instrumental in developing what you will not see in the talk, but very critical in the experimental aspect, sort of the formalism of how the way that we do this experiment isolates a multi-quantum coherence that is what we use to then quantify the Biexciton resonance. So from the formalism point of view, very key contribution from Raven. David Valverde Chavez is a postdoc who was very active in data acquisition as well as the analysis. Hongmo Lee did some DFT calculations in collaboration. Here we are with Sergey Tretiak. Oops, I'm sorry. Let me just. I'm not going to update anything here. If you can see the cursor, sorry. Sir Tretiak from Los Alamos National Lab. We have a collaboration with him, and he supervised Hongmo for the calculations. And Hongmo is co-supervised by Natalie Stinglin and I. And the materials come through the processing through Natalie Stinglin. Now, the next speaker, Eric Bittner, he is very, of course, very central in this work. He's one in terms of the intellectual development of this project. He is responsible for that along with me. He will present theoretical work in the next talk. And two former postdocs of mine who are now at Wake Forest University as assistant professors were part of this work, particularly in setting up the experiment and conceptually as well as initially the actual setup. And I want to acknowledge them as well, Ajay and Ilaria, assistant professors now in the Department of Physics at Wake Forest University. Okay, now with the important parts out of the way, let me just introduce some of the key concepts that I want to treat today. We're dealing with conjugated polymers, so polymeric semiconductors that form either a semicrystalline or a liquid crystalline microstructure. So semicrystalline as in polymer that a lot of us have worked with, P3HT, And this work that I'm going to now go through was developed mainly with P3HT in collaboration with Frank Spano and myself. This is really Frank Spano's work that is summarized in this annual reviews of physical chemistry that I cite here. The idea is that you can photophysically consider these materials as hybrid HJ aggregates. So we look at the photophysical aggregate literature from Kasha's development. We're very well, very mature in the photophysical, molecular photophysics community. If we have a set of chromophores that are aligned in such a way that their transition dipole moments align in a head-to-tail fashion, here we have what would be like a hopping integral. This is a resonance Coulomb sort of interaction between chromophore, chromophore, chromophore that has the way that this works out, head to tail coupling, kind of this hopping integral with negative sign. Okay, and so we would lead to an exciton dispersion that has a minimum at the k equals 0 point. We can excite the exciton. Now, instead of having a collection of transition dipole moments, we have sort of an addition, in-phase addition of the transition dipole moments. This is called a J aggregate, right? We see a line narrowing of the emission, and it usually corresponds to a redshift with everything else being equal. Alternatively, if you have cofacial couplings, this would be an H aggregate. We have kind of something happening here, but we have an inversion here of the sign, and now this k equals 0 transition is not allowed. Now we only can emit from this extreme point of this Brillouin zone like, and so we now have a forbidden transition that is vertical. This is an H aggregate, and in polymers where we have chains that may align in a cofacial way, we can have an intrachain exciton dispersion, but we can also have an interchain exciton dispersion, and that is what we call the hybrid HJ aggregate, and that is really the situation, and the interplay between these forces really determines what the exciton coherence length is along the chain as well as between chains, and so this is what we describe in this sort of two-dimensional coherence function here. Now, this is all that I'm going to say about aggregates and polymers, other than they are hybrid HJ aggregates. And because of the hybrid nature, we can turn an H aggregate into a J aggregate. Here's P3HT, and we can do this with the same material, the same batch. P3HT becomes an H aggregate it is predominantly an H aggregate when we cast it just from solution. But we can do some processing tricks, and Natalie Stingel, there are very well-defined ways to do this, where we can turn the same material into a J aggregate. This is not the same batch, but we can do that. So we can H aggregate, the signature is suppressed 0, 0 with respect to 0, 1. A J aggregate would be enhanced 0, 0 to 0, 1. And I should say H-like and J-like really to describe that we're in one limit or the other. So now let me turn to Biexcitons. I will just tell you that direct evidence, spectroscopic evidence for a Frenkel Biexciton. Now the question is, if we have two of these excitons, how do they interact to form a bound two quantum state? Does that state exist? What is its binding energy, and what is the nature of these bound states? If we go to the Vannier exciton limit, this is very well defined. We can find with linear spectroscopy very well defined signatures of Vannier Biexcitons. We can quantify binding energies. We know what the relationship of Biexciton binding energies, and let's say gallium arsenide quantum wells, is with respect to the exciton binding energy, and it's very well defined. We can identify them and measure them. Not so in organic systems with Frenkel Biexcitons. There is one report of a Frenkel Biexciton spectrum in an aggregate. In Frenkel Biexcitons in cold atom lattices have been studied as model systems, but in a, say, messy organic system like ours, do we have evidence or measurement of Frenkel Biexciton? The answer is no. And so, but there is indirect evidence. This is some work that I did a long, long time ago, where if we just excite sequentially to a two quantum state, we know that there are states there that 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 split up into triplets. They can undergo singlet fission into triplets. They can separate into charges, and this all happens sequentially in a two quantum state. What is the nature of these states? We don't have a direct measurement, and so there are scant measurements, but we do have questions that are important because these states we know that are important in things like exciton bimolecular annihilation. One of our chairs was very key in developing that originally with organic systems, singlet fission, singlet fusion as well. And so two quantum states in these systems are fundamentally photophysically very important. Can we get a direct measurement of their spectral signatures and characterize them? That's what my long-winded introduction is. So now I'm going to not tell you about the technique. I'm going to just say that I use a two-dimensional spectroscopy technique where I take a sequence of femtosecond laser pulses, 4 pulses, with a very well-defined phase relationship between a pair and another pair, 2 pairs with well-defined phase relationship that I defined by acousto-optic phase modulation. So these are phase modulated, these are phase modulated. I then excite to a 4th order population that I detect through photoluminescence, and I can demodulate that with a lock-in amplifier, knowing very precisely what the phase relationship is of the signal that I'm measuring, and I can construct a nonlinear signal that way. So here the idea, that's not what I'm going to talk about, but if I tune my laser to, for example, be overlapping 0, 0, and 0, 1 transitions and measure the time integrated photoluminescence, I have one energy axis that is defined by a pair of pulses, another energy variable defined by the other pair of pulses through the delays. These are coherent delays, and then something like a pump probe delay, population time. So I can measure population dynamics, but importantly, I can measure a two-dimensional spectrum that allows me to then look at spectral correlations, and that's what I'm going to be looking at today. And so I'm going to apply that technique, but I'm going to demodulate not only at some combination of, I'm going to modulate the frequency of the phase of this and the frequency of this pair of pulses as well, and I'm going to demodulate at a combination of those, but I'm also going to look at a harmonic of this. So don't worry about the details. The point is that I can measure two quantum correlation as well. And what I'm going to be looking for is if I excite coherently a two quantum state, what is the excitation, what is the photoluminescence excitation spectrum of that two quantum state versus a one quantum state. And so what are the spectral line shapes that I'm looking for? If I'm looking for in this two-dimensional spectrum, let's say that I have two transitions, let's say 0, 0, 0, 1, that's a little bit different from what I'm going to be seeing in a minute, but let's say two transitions, and I just do a regular 2D single quantum experiment, I'm going to see one resonance. They're correlated because they have a common ground state, so I expect to see a cross peak between these two. So this diagonal, one energy versus the other energy axis, are the resonance that I see in linear spectroscopy, but I also see correlations that they share a common ground state, for example. But if I do a two quantum experiment where I'm measuring a correlation now of my two quantum excitation with a one quantum excitation, so now I have two transitions, XA and XB at same energies here, but the two quantum correlation, I need to see if I see a peak that is above or below the rest of this two quantum diagonal. If I'm at the two quantum diagonal, this means that the two quantum energy is twice the one quantum energy. I just have two excitons and no interaction. There's no additional energy associated with the fact that I have two excitons. But if I see a peak that is below the two quantum diagonal, it is an attractive interaction. The energy of the two quantum state is lower than the energy of the one quantum state. Whereas if I see a peak that is above the two quantum diagonal, then it costs me energy to have that two quantum state. I get two excitons that I correlate, and the energy of that state is higher than twice the energy of the one quantum state. these are the signatures that I'm looking for. So because I'm running out of time, I'm going to quickly just give you the results, and Eric is going to go further into this. I'm going to now look at this polymer, PBTTT. This is now not P3HT. The reason we choose this is because it's like P3HT, but it's at some high temperature, it's going to have a thermotropic phase transition. It's liquid crystalline. It renders this a very dynamic system. Our line shapes in the 2D spectrum are going to be very, very well defined because dynamic disorder is going to dominate. And so that's the rationale for choosing this. But it looks like P3HT. If I look at the absorption spectrum, I see a suppressed 0, 0 compared to 0, 1. This looks like an H aggregate. And so this is kind of like P3HT. So here's the picture that I had. Here's the data. Now, the way my laser spectrum is tuned, I'm covering all. I wanted to cover all of the 0, 0 line, and I'm slightly overlapping into 0, 1, but I need to cover all of 0, 0 line for a reason that you'll see in a minute. And so what I see here, this peak here, is this diagonal peak. This is a 1 quantum 2D spectrum. This diagonal peak is the peak of 0, 0, okay? Now, I don't have enough bandwidth to really cleanly see 0, 1, but I do see these cross peaks that are cross peaks between 0, 0, and 0, 1. That's what I expect. But I also see some very weak structure at lower energy in the diagonal, and then I see strong cross peaks with the structure. It turns out that when we do this trick with Natalie Stingelin of turning the H aggregate into a J aggregate by essentially blending it with a very polar polymer, we can have the predominantly H aggregate in PBTTT or P3HT become a predominantly J-like aggregate. We see that the 0, 0 in those systems shifts from here to here with some structure. So we're going to assign these things as kind of a weak signature of the J aggregate in this hybrid H system that we always expect. Now, the key result, and this is where I will sort of emphasize, the key result is that when I now do my 2 quantum coherence experiment, so this is a 1 quantum coherence, here's a signature of the 0, 0 of the H aggregate, here is a weak signature that we interpret as a 0, 0 of a J aggregate, here's another peak that is another progression perhaps of the J aggregate, strong cross peaks with this. We go to the 2 quantum coherence. This axis now, you notice that the energy is twice the energy of this. This is a 2 quantum coherence that we select out by our phase modulation scheme. And we correlate that with the same 1 quantum coherence from our other pair of pulses. And we find that the 0, 0 peak is lower in energy than the 2 quantum diagonal, okay? But these lower energy that we ascribe to 0, 0 of the J aggregate are higher in energy. How is this? Basically, we're expecting that, let me just skip over this. We expect that if the interaction energy, that this J, or here we call it a T in Eric's work, if T and U are the same sign, we will get a bound Biexciton. But they can be a negative T, a negative U, or a positive T and a positive U. And the really surprising thing is that what you have for a J aggregate is kind of inverted for the Biexciton. If we have a J aggregate here, so we have an exciton kind of dispersed along the chain, the way that the Biexcitons will interact will be with a flip side of the T's and the U's. So the J aggregate exciton wants to look like H aggregate Biexcitons. And conversely, the H aggregate exciton wants to feel like a J aggregate Biexciton. So that when we look at these correlations, this thing that is at the peak of the 0, 0 of the H aggregate gives us a negative correlation, whereas and normally we would say that sounds like a J aggregate, whereas this thing that we ascribe to a J aggregate, the 0, 0, gives us positive correlations that we normally would ascribe to an H aggregate. So here's this inversion. This is what Frank really likes to call the Jekyll-Hyde aspect of these polymers, is that they are hybrid HJ aggregates, and the H-like exciton sees itself as a J-like Biexciton, and the J-like exciton sees itself as an H-like Biexciton. And that was something that we didn't expect, but it's something that we would interpret from this data. And I think it follows nicely some of the theory that Eric is going to talk about. So I'm almost out of time. I'm almost talked for 20 minutes. Let me just point out that if I take a cut here in the 0, 0, what would be the 0, 0 of the linear spectrum for the H aggregate, this is a 0, 0, a cut of the 0, 0 of the J aggregate in the linear spectrum. I can then see that there's a distribution, and then plot the amplitude of this cut versus the relative energy in this 2 quantum energy axis relative to the diagonal. So 0 is the position of the diagonal. So below, that's a binding interaction. Above, it's sort of it's an attractive binding interaction. Above, it's a repulsive binding interaction. And I can see that my 0, 0 H aggregate-like thing is bound at something like 60 or something millielectron volts, but there's a distribution. These, what I would say, the peak of the J aggregate exciton has something of the order of 100 and something millielectron volt repulsive energy, and then there's a distribution. And so we can quantify the binding energies. We can now look at this as a function of microstructure, other parameters, and that's something that we're very excited about right now. So I'm out of time with my 20 minutes, and so I'm just going to skip to these conclusions. What I want to leave you with as a take-home message is that Frenkel Biexcitons in PBTTT can have attractive or repulsive binding. Binding energies of the H-like exciton is about 60 millielectron volts, quantified by that 2 quantum measurement. And then we find, this is really the bit that surprised us, that excitons with interchain bibronic dispersion, what we call an H aggregate, reveal intrachain, so J-like, biexciton correlations and vice versa. So with that, thank you again very much for the invitation and for organizing this, not just today, but this whole series. And I'm very happy to take questions. I just want to point out that we do, none of this is published, but we do have this in the archive. Probably not yet in the form that how we will submit it. It will be updated, but you can look it up if you want to look at this work a little bit more. So thank you very much.
Right. Awesome talk. Thanks, Carlos. We do have time for a couple of questions, and we'll try and keep them on the experimental. And the first one from Suggy, our host, is do you see exciton annihilation dynamics? So
I didn't emphasize what I should have, because I was trying to rush through this. I'm going to say that every spectra, and I only showed you 2. So these spectra that I showed you, they're all at the 0 population waiting time, and they're, well, 0. I mean, we technically not, because we at 0 time we have ambiguity time ordering of the pulses, but they're like a pulse width away, something like 20 femtoseconds away. And so they're at very early time. So there hasn't been enough time for any population relaxation. So this is essentially 0 time. And and I'll also mention that this is at 5 Kelvin. At room temperature, the story is the same. It doesn't change. Of course, the spectra are a little bit sharper, nicer at 5 Kelvin. So in these spectra, there is no population signature of bimolecular annihilation. I'll also mention that the fluence here is of the order of, I think, something like 30 nanojoules per centimeter squared. If we do a pump probe experiment at this one, it would be relatively minimal. We can go to higher fluence, and we see that. And in fact, that's something that contaminates the line shape in ways that are kind of an additional incoherent contribution to the line shape. But the point is that there is also a way through the line shape to tell whether there are bimolecular annihilation effects. And at this point, they are not dominant, but we still, of course, see the exciton biexciton correlations.
Okay, so you anticipated the next private question, which is, what are the intensities and what are the excitation densities that you're using for these experiments?
Yes, so in terms of excitation densities, I should have run it through it, but the fluence is in the order of 30 nanojoules per centimeter squared, which is which is about a factor of 100 lower than I think typical pump probe experiments are in the low fluence range. I mean, not nowadays, maybe that's not, it's at least a factor of a few tenths. So we were definitely in a low fluence regime, where like I said, we know that through analysis of this line shape, but also through our own population dependence measurements, exciton by molecular annihilation is not a dominant pathway.
Okay. And then, this is actually a question for me. I'm relying on my old memory, right? There's these old tools that people use to detect Biexcitons in inorganic semiconductors, Vannier Biexcitons. And like, I think copper chloride maybe is one of those systems. And I think it was, they use sort of standard luminescence techniques. Of course, those are Vannier excitons. But why, what's the barrier for applying those traditional tools to the organic systems?
I mean, it just seems like what in the Vannier Biexcitons, the photoluminescence signatures were very easily. You do a fluence dependence PL measurement, and then you see peaks that grow in with fluence that have quadratic dependence, and you assign them as a Biexciton as such, and they're very spectrally well defined. That doesn't appear to be the case in these systems, largely because of heterogeneity, but also I think what we might begin to understand from this is that there's also a very complex set of correlations that it's not clear whether you should always get a red shift or a blue shift, and they may be small, and on top of kind of our large and homogeneously broad linear line shape, but they're probably very difficult to make out. And so that's my sort of gut answer.
Okay.
And I think I mean, if you look at the spectra, the kind of the energy ranges compared to say what your total line width is, I think supports that view.
Okay. And then Sagi, I'll rely on you to tell us when we should stop, but there are a couple more questions.
We have 4 more minutes.
4 more minutes. Okay. So
Yes.
Carlos, the clock is ticking. From Kathy Wong, do you anticipate that this will be a general phenomenon for Biexcitons and HJ aggregates, or does it depend on the exact couplings?
That's a very good question, Kathy. And I will just disclose that that's a subject of a grant proposal that is right now for review. And here's the deal. I didn't talk about these, but these are DFT calculations on the left-hand side from Hongmo. This is the work that we're doing in collaboration with Sergei Tetrek at Los Alamos National Lab. And basically, in this system, we don't have a really large permanent ground or excited state dipole. What we show here are kind of in this particular conformation for this trimer, we have a ground state and an excited state dipole that is orthogonal to this. This is a transition dipole moment, right? And of course, this is fluctuating, and these dipoles are fluctuating all over the place. Now, let's go to push-pull material. These are going to be pretty big.
Actually,
yes, sorry.
Carlos, I'm going to interrupt right there because I think we're going to run out of time. And there's a private question, and Eric also said he would address this in his.
Okay, perfect.
So I'm going to jump to a different question, which says, do you see vibronic dynamics decoherence, and what is the time scale?
Okay, so I didn't show you this, but we have a separate body of work that's paper that I'm happy to show you. Well, it's not quite yet on the archive, but it will be soon. We're still sort of finishing our draft, but there where we look at the phasing dynamics, and we see very, very interesting things that if you look at 0, 0, 0, 1, they're different, and that's effect. Moreover, we see a line shape. If we now decompose this 2D spectrum into the real and the imaginary part, absorptive and dispersive part, we see that 0, 0 invert the character in that 0, 0 looks absorptive at 0 time, but becomes dispersive. 0, 1 looks dispersive, but becomes absorptive in a time scale of 100 femtoseconds or something like that, which is roughly, something like, well, the phasing dynamics like 50, 60 femtoseconds. So that the phasing definitely is very, very sensitive to the fact that it's an aggregate, and the details of the aggregate are that's electronic defacing. Now we also see by Brownick coherence that oscillates not at the frequency of the carbon-carbon stretches, but we see at some lower frequency that we assign as some sort of torsional-like mode. And we're not quite done with this assignment, but this is sort of what's leading also some of the vibration by Brownick defacing dynamics in the system. That's a separate body of work.
Okay, and then I don't know if we have any time left for Naomi's question. Very quickly, what might be the impact be of the fleeting biexcitons when these polymers are used under operating conditions? In other words, what do you anticipate the sort of practical consequences, I guess?
You know, in an operating condition, the spectral density is going to be very different. You know, if you have a charged background, as in a device, of course, these dielectric fluctuations are going to play a huge role in the defacing. We know that. And I don't have a very satisfying answer to that question. What I can tell you is that this experiment we can do with photocurrent detection, so in a device, and that's an interesting thing for us to see how these exciton biexciton binding properties and dielectric fluctuation, well, how they are affected by the kind of the operating conditions you would expect in the device.
Sounds good. I'm going to turn it back over to you, Sagi, because I think we're.
Yeah. Thank you, Carlos.
Yeah, awesome.
Our next speaker is Eric Bittner from University of Houston. He is going to talk about theoretical aspects of Biexcitons. Eric, it's your turn.
Okay, let me share the screen, hopefully. That one. That one. And of course, my talk disappeared. Where'd it go? There it is. Is it on? All right, awesome. So I didn't know if Carlos was going to talk about that work or our other work. So I sort of prepared for both. So I'm going to skip over and maybe just give a highlight of the other work. And there we go. And for whatever reason, LaTeX wants to show you both slides at once today. I don't know why. You get to see the preview. So maybe just a little bit of sanity. I reported upon this last year, or this summer in Telluride. I actually built a boat under pandemic conditions. And it was a great way to do some social distancing, I will say. And it's a great therapy for distraction from everything else. So there's the Bittner boatyard, and there's the Bad Shasta boat out sailing in Galveston Bay. And I actually plan to take it out into the Gulf. We're going to sail to a barrier island over spring break. So that should be a lot of fun. And that'll be my second time out of that. Right there. I am out of Harris County at that moment, right there in that photograph, officially. Some other work that Carlos didn't talk about has to do with excitons in these 2D perovskites, and we did some nice work on that. But since he just talked about the other stuff, our more recent work, I'll just give you a quick little overview of what we did with some of his work on that. He can talk about more of this. But what was interesting was that the dephasing time in these low-dimensional systems depended upon the fluence. And so we wrote a couple papers last year where we developed a new stochastic calculus-based approach to study this sort of transient dephasing effect, that as the background population evolves, the dephasing time becomes longer and longer and longer as you wind up with less and less stuff behind you to dephase you. So we use a really cool Ito calculus trick that I started playing with. It actually goes back to where I was in graduate school. I learned about this stuff, and it was sort of fun to pull this stuff back out. And so what we do is we model the background population as a stochastic background. We can work through with our paper on this if you want to see how all of this comes about. The long and the short of it is you wind up with something that dephase, at least with dephasing term, you can see this in equation 3, that depends upon both the instantaneous steady state fluctuations of the background, but also the fact that its background is is evolving and narrowing and doing all sorts of cool stuff at once. And we use Ornstein-Uhlenbeck for the background process, and it's simply a mean reverting stochastic differential equation. We could pick other ones if we wanted to. This was the one that we chose. It corresponds to like a Brownian motion type dynamics, and DW is, so the really cool thing from Ito calculus is this isomorphism between DT and DW squared of the noise kernel, and it's a nice thing, and you can derive other correlation functions from this if you want, and that's what we do. We derive linear response. There you go. And since I want to talk about the polymer stuff, I'm going to just leave this, and you can go through it at your will. The cool thing about the Ito calculus is that it's a really powerful way for evaluating these multiple time intervals that you see in these, the sort of typical Mucomelia correlation functions that we all like to derive. And it gives you a nice way to tie in an arbitrary stochastic dynamics or stochastic differential equation that describes your bath, if you would, into directly into the spectroscopic response function. And so we can compare to Anderson-Kubo theory, and that's what we do over here on the right. That's the linear response. That's for a stationary background. If you have a non-stationary background, you get this really wild and wacky results that can show Biexcitons and other sorts of cool things that come about. You get suppression of the initial background due to peak absorption intensity. You get a blue shift because of the increased number of scatterers. You get a broadening and all this kind of stuff. And anyway, you can look through our paper and discover it. We, of course, we can calculate double-sided fiber diagrams for this kind of stuff and compare to Carlos's theory. And I know I realize I'm going super fast through that. I'm on deliberate. But let me get to the cool thing here, and that is this big white screen that has, it's a picture of Eskimos in a snowstorm. No, it's not. The key thing is over here on number 17 is the exciton line shape that we calculate from our model and eventually correlate this to the results in Carlos's experiments. But what's interesting, you see both this evolution of the line shape and its narrowing as you increase the waiting time. So, almost with no parameters, well, there's some adjustable parameters we could try to fit if we wanted to, and to get the exact spectrum, and that wasn't the goal of this. It was really to try to explain the general features of these rephasing spectra that Carlos was saying. And I think we did it. We get it right. Anyway, now going back to Carlos's talk. So thanks, Carlos, for a great 20 years or so of collaboration. I just want to say that I think Carlos and I met each other in 1995 and dealing with solvated electrons and all that kind of stuff. Anyway, so these Biexcitons are consequential. Many of us know that. And responsible for all sorts of interesting dynamics, specifically in organic semiconductors, which is what most of us in this particular seminar series are interested in. But it's an important intermediate in lots and lots of kind of processes, and which I list here. And many of you all out there study those. And so Biexcitons are sort of interesting things. This is a picture from Carlos's talk, which will be in our paper, I hope. In that H-excitons, which Carlos gave a great overview of, are more or less aligned perpendicular to the chain. They stack like this, but if you think about it, they must move parallel along the chain. And likewise, J-excitons are aligned perpendicular to the chain, but move aligned parallel to the chains, but move perpendicular to the chains. And so that tells you right there that the hopping integral in the different directions for an H-exciton, taking that as taking the exciton as the quasi-particle, is different depending upon if you're an H-like, more H-like, or more J-like in your behavior. And so to describe this, we developed, this is what we do. So Carlos comes up with a cool experimental result, calls me up on Skype and whatever, and then we wind up talking about this, usually with some whiskey involved to catalyze things or some other sort of beverages involved, and come up with an idea to understand all this kind of stuff. So I over Christmas, I couldn't go, not over Christmas, over Thanksgiving, I couldn't go sailing because the weather was crap. And so I started playing around with those lattice models, and and work this following thing out. So if you take like a one-dimensional Hubbard model that I show here in equation 9, if you just drop off the last term with u, you simply have motion along a lattice. In delta, I added to emphasize the fact that, you know, if we're dealing with the copolymer system, you have an energy offset between site A and site B, which at the time I thought would be interesting to look at. And so I refer to this as the crenellation of the potential surface. And so it's simply the fact that you're dealing with a copolymer system that might have an energy barrier between the different sites. And so you can have, you know, if I look at the bottom pane of that figure, I can have an unbound pair of excitons. The little stars will be the excitons, localized on site B, for example, and those would be an unbound pair. So the contact interaction U turns on if I have excitons that are on an adjacent site, either on site A and B or BA, it doesn't matter. But two excitons that are on non-adjacent sites are going to be considered non-bound within this very simple Hubbard model. Now we have not done the two-dimensional version of this, but it's relatively straightforward to adapt. But you know, so Carlos had this really interesting point that maybe I didn't appreciate at the time, and we hadn't thought about it in this framework. But you know, if you think about this T as a something that's like the prefactor for the kinetic energy operator in a one-dimensional Schrodinger or any Schrodinger equation, you sort of wonder if this sort of strange result that you know, here's a one-dimensional Schrodinger equation for a delta function potential. And if I take T as minus h bar squared over 2 mu, the reduced mass, so long as T and U have the same sign, I still get a bound state, meaning that the bound state wave function decays exponentially away from the contact potential. Now, the sign of U and T, it doesn't matter as long as they're the same sign. You get a bound state. You get an exponentially decaying state. So you can have T less than 0, U less than 0 to produce a bound state, which would be the typical case for a positive effective mass. Or you can have T greater than 0 and U greater than 0, which would correspond to a negative effective mass and also produce a bound state. So in one case, you're going to drop down below the energy continuum, which would be the typical case. But if you can also pop up above the energy continuum, and there you go. And you can be a bound state. So on the right-hand side, I show the exciton radial distribution for a model for the 1D lattice for increasing crenellation, and the crenellation breaks things up. And so if you just simply can't get close enough because you wind up with two wells with a barrier in between. If you have very, very strong modulation of the potential energy between sites of your copolymer system, and that actually is the origin of this waviness. Is that you know, I'm low energy, high energy, low, you know, attractive, you know, et cetera, as I move down the chain. But this blue curve is the result that you would get from the one-dimensional Schrodinger equation without the crenellation. So what you can do then is you can take this and just analytically come up with a parametric threshold for the formation of bound excitons. Just simply say that, well, I know that the model is going to tell me what the threshold for free exciton pairs must be. Let's take U equals to be 0 because they're not in contact with each other anymore. That's an asymptotic limit, and you wind up with this sort of plateau. Okay, delta is the crenellation, T is the hopping integral, and this is the constant. So long as so if you're below or above 4, depending upon if you're a positive or negatively attracted system, there you are. But you can bound states as soon as you cross this threshold. And so as soon as one of the questions what was earlier was, is this a universal effect, or is this something that's unique to the system that Carlos was looking at? If you take the values that Carlos had, and we believe the binding energies and everything else, and I just went backwards the wrong way. There we go. We actually wind up fairly high up into this bound exciton curve for this PBTTT system, and we're doing a sort of a literature search, I guess is probably the easy way to think about this, for a search for Biexcitons at the moment, and eventually turn this into an experimental like phase diagram. So looking for what menagerie or what sort of stability criteria are going to be needed for a wide class of conjugated polymer type systems. And so that's something that, so Carlos mentioned, yeah, we're writing a proposal on that, and that's what one of the outcomes of that project will be, hopefully, if we get funded. If not, we're going to do it anyway and just not tell you about it. I mean, I will tell you about it. But then the other question is the effect of the static disorder, energetic disorder, because, you know, all of these conjugated polymer systems are in a noisy, static, noisy environment. And, you know, there's fluctuations and there's stacking differences and all sorts of kind of stuff that's going on. So one of the questions we were interested in is how stable is this Biexciton to just simple energetic disorder of the system? So what I show on the curves is is basically the increasing of the interaction from very strongly interacting to very weakly interacting for a given case for a given model of the system. And what's interesting in this is the curves that are at the top, and unfortunately I can't point out things on this. You can see my hand waving around maybe. The red curve, all the way down to the yellow curve, are all the cases that would correspond to the bound, sort of like energetically bound Biexcitons, where we really do have this attractive potential or this U term kicking in to cause you to force the two excitons to be right next to each other. There's a threshold point at where this value is around 2.35 for this system, where you no longer can form kinetically bound Biexcitons due to this interaction. However, what can happen is that because you're dealing with a disordered lattice, you might have just fortuitously find two A and B sites that have been both pushed down and pushed up that form a little attractive well, and you can localize there. And so what you see is at very high amounts of disorder, sigma being the disorder, is that these sort of kick in of localized bound states. And we haven't done any sort of analysis of what those states would look like or anything like this. This is still fairly, like Carlos said, this is all still in the preprint form, and we're talking about this in probably the tip of the iceberg of a multi-year study. But you know, going back to Carlos's talk, yeah, this is the segue into Carlos's talk. I think we see pretty strong evidence for these kind of states in his 2D spectroscopy. Whether or not this is unique to this particular system, I think remains to be seen. I think it's amazing that both 2J and 2H species can be seen in the same sample. It's interesting that these Frenkel Biexcitons were predicted, you know, long ago. ACKNOWLEDGEMENTS and et cetera talk about this stuff in organic systems. You know, a long time ago, early 90s. You know, Frank and ACKNOWLEDGEMENTS and Frank Spano, ACKNOWLEDGEMENTS, and Shel Mukamel have a paper on Biexcitons, but nobody's ever seen Frenkel Biexcitons. I should say that only a few cases have ever been seen in, like for example, in solid argon, atomic lattices in optical cavities. It's just such a difficult thing to see. But they're readily seen in quantum dots, of course, the 1A excitons. So this is sort of an interesting observation, and I hope that we get our paper published in a high-profile journal that begins with S sometime in this year, whenever. Anyway, I want to thank my co-workers on all of this, my postdoc Hao Li, Carlos for, you know, ages of conversations and et cetera. I didn't talk about the work that I've done with Andre, and of course Ajay is starting off as a new professor in Wake Forest, and these are the references to the papers we had, and I'll open up the discussion to I see Natalie giving me a thumbs up. That's awesome. I don't think she's watching the talk, but anyhow, I'll open for discussion. Thanks.
All right, awesome job, Eric. I think this is a nice bookend to Carlos's talk, and I'm just going to start right off with the questions from Mark Wilson. What are the possible limits on the quote-unquote Frenkelness of the Biexciton? In the cartoons, the H-like character was motivated from excitations on adjacent chains, each of which had J-like coupling. Do we require the adjacent chains to see mixed character, or could there ever be enough wave function extent on a single chain to plausibly host a Biexciton with combined JH effects?
That's a cool question. I don't know the answer to that, and I was thinking about that because I saw that, and I think that's something that we're hoping to try to address. This U interaction seems to be the key, and that's of course a related to like a Coulomb or dipole-dipole interaction between the two different excitons. You know, the H-ness versus J-ness. You know, I think that the other aspect of that is probably the charge transfer character of the exciton as well is going to have a huge impact, and probably a bigger impact on the ability to form biexcitons, because of the fact that if you have charge separation along the chain, you can get different kinds of stronger interactions, I believe, for this U term. I think the dominant character of the system is what's going to be the determining factor of whether or not it's going to form H-like, double H or double J, I should say, biexcitons. And I think these are very idealized systems as well. You know, this is probably why you don't see biexcitons easily at all, as in like anthracene or small molecules, because you do get this sort of delocalization of the exciton across multiple chains. You're probably looking more like a, you know, a delocalized blob instead of a more linear dipole along the chain. So I think that's a hand wavy explanation of this, but I don't have any hard numbers to back that up.
Okay, well, you can continue with the hand waving because I'm going to skip ahead to another question, which is, what is the physical meaning of the contact potential U, and does it involve permanent dipole-dipole interactions?
No, I think these. If you look at the cartoon that was in Carlos's talk from the DFT calculation showing the orientation of the transition moments, I think that's the dominant thing, is that these, you know, if you look at the permanent dipole moments of the excitons themselves, they're pretty small and actually oriented and almost perpendicular to the chain itself. And so I think that's a fairly minor effect. I think the bigger issue is probably, of course, that's also super dependent upon, you know, any sort of like bowing or twisting or whatever of the polymer chain itself is going to push the orientation of those dipoles, the static dipoles, all over the place in these systems. So I think the dominant effect is probably the stacking of the transition moments rather than the permanent dipole moments. So it's sort of more of that effect. But that's a cool question, and again, it's just that's my gut answer. It was one of the things we wanted to get out of the DFT calculations, but doing DFT calculations with biexcitons is so far good luck. Good luck on that one.
Okay.
Well,
yeah. Maybe we'll return to that. Now, here's a more specific question: is the background noise in equations 3 and 4 real valued? So this is a somewhat
that is
specific.
true. Yeah, those were populations, because and yeah, those were populations and not quantum operators. So in our theory for that, if I can go backwards a lot, that's the Eskimos in the snowstorm. Good job. Or Eskimos in the snowstorm. It didn't like that. Okay, don't do that so fast. Yeah, in 3 and 4, yeah, and the reason is in equation 2. When you work through the many-body theory for this, you wind up summing over all of the terms that are of k not equal to 0. For example, let's take those as our background. There are other terms that are of higher order that would correspond to the fluctuations out of the k equals 0 term, like that would give rise to like Bogolubov excitations in bosonic systems. But the leading order term in all of this was simply like the sum over all the background population states. So if you take that as a collective variable, that's a real valued collective variable. And that's what we do. So equation 2 is already, that's why we've got a wavy line right there. We're throwing out those sort of coherent fluctuations, correlated fluctuations, and all that kind of stuff, because I don't think they're certainly there, but they're much weaker effect, and it's certainly not going to be visible in an ultrafast spectroscopy experiment like what Carlos is doing, and so probably not relevant for this kind of calculation.
Okay, so closely related to that question, can you validate a noise model from direct microscopic computation rather than depending on comparison to averaged experimental results?
Yeah, and exactly right.
And what kind of computation could you do?
Well, if you need to know the density of states of your background, that's the first thing that you need to do. And the second thing is the coupling to the exciton itself. So again, if you think about the noise kernel that's in equation 4, I mean, you can calculate and show. I mean, maybe I can, if I go forward one slide, you don't see it, of course. Okay. Anyway, there's a correlation function that's in there. If you knew the autocorrelation of the spectrum or of the background, that gives you a spectral density of the background. So there's two things you need to know. There's the spectral density of your background, and you need to know how those states are populated by the fluence of the laser itself. And so in the model we use, we assume that you've got just a Lorentzian background for the spectral density, and then just a broadband coverage for the laser. But yeah, you're right. You could go back and use a more complicated spectral density for the background and the laser, and have a more physically close model. But my guess is, when you sort of integrate, you do everything else, and you do all the calculations at the end of the day, you're probably going to be really close to the Ornstein-Uhlenbeck model. There was a couple models that we're thinking about. Is probably more of like a geometric Brownian motion model that allows you to take into account that as your system relaxes down to the steady state, the fluctuations in the background also decay. So this is one of the problems with Ornstein-Uhlenbeck is that you can get to in this model is that you can be a zero population in the background, but still have noise which makes no sense. And so the mean reverting model for the density or the number density is probably not great. It's something we can analyze, but we can also analyze this geometric regression. And the nice thing about this stochastic model, if I could throw in one more plug for it, is most of the mathematics, and for that matter, most of the computational tools that are developed for this are developed in the field of quantitative finance. And so we've been doing a lot of field mining, if you want to put it that way, learning computational finance and quantitative finance in our group to pull out some of these really cool Ito calculus techniques that are in that field. And maybe, I don't know, we go off and buy GameStop or something. I don't know.
All right, now this is a first. The financial world is bringing its mathematical tools to science. We'll see what happens with that. This is a related question from Suggy, which is a question about the Ito calculus. Is it physically plausible to assume that there are stochastic processes with randomness of correlation times, or with correlation times that are even shorter than the quantum decoherence time? And I guess presumably that's that.
Yeah, well, I don't know. I mean, that's right. It's a philosophical question. I mean, there is always an assumption in all of this that that you're sort of throwing away the coherence in our model. Is you're throwing away coherences between the system and the environment. At the end of the day, that is true. I suppose we really wanted to be more careful with all of this. We wouldn't do, we look at the more higher order terms, and you look at how do A and A dagger themselves evolve, so you would get the complex phase behavior as well in the stochastic model. I mean, people in optical physics and quantum optics have dealt with quantum stochastic equations for 25 years or probably more, 40 years. Mostly in the field of treating quantum photons as stochastic operators. And so there's a lot of, again, field mining that we can do to maybe address these issues of how do I put in the dephasing and phase dephasing between the system and the bath. I guess in our model, we're more or less assuming that there's an instantaneous dephasing, quantum dephasing between the system and the environment, but it's inducing dephasing within the system variables themselves. And I think that's not a bad or unstandard approach. I think any sort of master equation approach that you're doing is going to eventually wind up giving you that kind of dynamic. So you could probably, if you wanted to, push it a little bit more, calculate a master equation for our A and A dagger variables and integrate over the bath, and you would have like a Nakajima-Zelinsky equation for the system variables relative to our bath. And so, the goal in this particular calculation was to take advantage of the fact that, or to include the fact rather, that the bath itself is non-stationary. And that's why we needed to use this. Well, we didn't need to. It was very convenient to use this Ito calculus and mean reverting approach. It was also just sort of one of these things I found to be intellectually interesting to play around with it. And to be perfectly honest, when we were working in this outlet last summer, I thought this was going to go nowhere. I thought this was just going to be fun playing around with some fun mathematics. I really did not think it was going to have any relevance to Carlos's experiments.
Okay.
To be honest. Yeah. Okay.
Nice to be surprised in a good way.
Yeah, exactly. So it doesn't usually work that way.
Okay. I think we're gonna move on to the next. We're gonna actually shift. So let's thank Eric again for really Eric and Carlos for really nice talks on singlet Frenkel singlet Biexcitons. And I think now we're gonna shift a little bit to Frenkel triplet Biexcitons. If I predict correctly, Matt's talk, and eventually Ranier Biexcitons with Lawrence. But let's Matt, if you can post your talk.
Yeah, sure.
And we'll be ready to begin.
All right.
All right. It's very general Biexcitons, but we'll see what type.
Right. So I tried to choose an ambitious topic, then realized it was 20 minutes. I tried to back out, and Sugi wouldn't let me. So anything unclear, you can blame Sugi. Right. So this is meant to be a summary of effectively 5+ years of work in my group in collaboration with Luis Campos at Columbia in using individual molecules to investigate the spin properties of Biexcitons and understand how the spin properties affect the recombination dynamics. So I'm going to try to hit just the highlights, the very high level stuff, and we'll see how it goes. I should finish. In order to finish this talk, I have to put up some very serious disclaimers. And rather than me read them to you, I will just put it up so you can read it and just say that there is a ton of work from actually many people who are members of this workshop right now, who saw as their name listed online, who have done similar work and reached similar conclusions. So I think when you see the conclusions of my talk, you will say basically everything you said is in the original Merrifield paper in 1970, and particularly the aspect of time-dependent dephasing and rephasing of triplet excitons and how the magnetization of the intermediate pair state affects the possible recombination channels. And so again, the proposal came in the 1970s, beautiful demonstrations of this in the 80s and early 2010s from Chris, one of our esteemed co-hosts, showing again just dynamic rephasing and dephasing of excitons in time. So I think again, the conclusions will look familiar. The way we get there is slightly different. We're going to do something. I really like this quote: "We can forgive a man for making a useful thing as long as he does not admire it. The only excuse for making a useless thing is that one admires it intensely." So we're going to intensely admire a set of individual molecules that really allow us to isolate these different spin states, the different spin triple pair sublevels, and really pull out the contribution of the individual sublevels to the recombination dynamics. So those are the disclaimers. There's a lot of work I do not have time to acknowledge that's come before this, that set the stage for all this. Where I'm pulling directly from that work, I will acknowledge it, but please forgive me if I didn't post your paper. Know that I understand you've done a lot of this work. So I think this is a useful point of comparison because, so what are we talking about? We're talking about using one photon to excite a Biexciton in a semiconductor system. So in an inorganic semiconductor system, this process has been studied, and it's simpler than the stuff we'll discuss in the organics, primarily because of we don't need to consider spin in terms of the dictating the fate of the Biexciton. So again, this is probably familiar to most people. You take a high energy photon, which creates a hot exciton in a semiconductor. Okay, and so your hot exciton has two possibilities to cool. One way it can cool using just conventional multi-phonon emission, relax to the band edge in the way you were used to, again, with most hot exciton systems, or alternatively can undergo a process called impact ionization, where instead of cooled by emitting phonons, it cools by emitting a second electron hole pair, with all the caveats about energy conservation coming into play. What's important to note about Biexciton formation, in this carrier multiplication regime, where again, we've only put one photon into our system, is that the yield of the Biexciton is a result of the competition between the normal one electron relaxation process and the impact ionization process, which produces our Biexciton. What's really notable in these systems is that the impact ionization rate is strongly a function of the initial energy of your hot exciton. The hotter the exciton, the faster this impact ionization will be. And so the yield of the Biexciton is a strong function of the input photon energy. And the impact ionization can go from a few orders of magnitude slower than cooling, carrier cooling, to something on the same order. Again, as we go up in energy, the impact ionization gets faster and faster. The end result of this, again, I don't want to spend too much time on this, but the end result of this is that if significant deviations from what you would call ideal behavior, meaning as soon as you have enough energy to create a second electron hole pair, ideal behavior would say you create that. And so on average, for every input photon, you would have 2 excitons on average. So real systems deviate significantly. In fact, the threshold is a little bit elevated from the thermodynamic limit. And then if we think about where we finally get to the limit where we have on average 2 excitons from one photon, it's several times the band gap of the quantum dot already. All right, so that's an important. There's efficient one electron cooling processes that compete with Biexciton formation. The other really important thing to note is that Biexcitons are not particularly long-lived because there's a really efficient Auger recombination channel where one of these excitons will annihilate by returning to the ground state. The other one, will gain the excess energy and just be hot again. And so, again, we can set all of these numbers depend, as things do at the nanoscale, on the shape and on the engineering, on the overlap of the electron hole. So these are just approximate numbers, but just to give you an idea of the orders of magnitude, that's about 100-ish picoseconds. Okay, nevertheless, people have demonstrated using photocurrent and other types of measurements that Biexcitons can be harvested, that you can actually use this carrier multiplication process and get extra work out of the photons you put in. And you can demonstrate that despite some, again, reasonable binding energies for both the exciton itself and the Biexciton. The exciton binding energy on the order of ½ a volt and the Biexciton binding energy on the order of 50-ish millivolts. So binding energy is greater than KT, yet still we can harvest them and use them without too much trouble. Okay. So what are we contrasting with in the molecules? Well, with molecules, we really have to consider spin. And what spin ends up doing is offering protection against competing one electron decay processes. So if we say that impact ionization happens under sort of low photon energy conditions, it's efficient, and our Biexcitons are short-lived, in our organic molecules where we have an equivalent process or analogous process called singlet exciton fission, we put a photon in, we create a cooled singlet exciton. Our cooled singlet exciton can relax to a triplet pair, and our triplet pair can dephase, and I'll show you later, do other things as well. So here, instead of Biexciton formation having to compete with carrier cooling, it has to only compete with some sort of, decay back to the ground state. And so we're photoexciting a cooled singlet exciton. So again, carrier cooling, it's already cooled in the sense of it's not easily able to relax to any low-lying triplet level. So, we'll have 1 nanosecond or 10 nanosecond decay times back to the ground state. And so we have basically 4 orders of magnitude longer to form our Biexcitons. And in addition, what we'll see is that the Biexciton decay is protected by spin angular momentum. And so instead of having 100 picoseconds just rates, we'll have things that I'll show you rates of up to something like, time constants of up to something like a microsecond. And then again, how does that manifest in terms of yields? Well, we can argue about device architectures and differences in terms of utilizing these extra, Biexcitons we generate with 1 photon, but we can just say, I think, and agree that in terms of generating triplet pair Biexcitons, organics exhibit this ideal behavior where pretty much as soon as it's thermodynamically allowed, you have on average 2 excitons for every photon absorbed in that molecule. Okay, let me see how I'm doing. All right, so we won't belabor this. The freshman chemistry picture of the 2 spin states is very familiar to us. You take a spin half particle and a spin half particle, and we couple them just via angular momentum addition, and we get a new set of particle states with 2 different possible magnetizations. So we have 1 net singlet and 3 net triplets, and the structure of those spins is again familiar from us for hopefully for everybody in this audience. Maybe slightly less familiar is this idea of what happens when you try to form 4 spin states. You can do the same thing. You can do angular momentum addition of 4 1/2 spins, or you can just take the combinations of the products of the 2 spin states. So we can have a triplet exciton coupled to a triplet exciton, a singlet coupled to a singlet, or singlet coupled to triplet in various ways. And then you get a new manifold of particle states. And the ones we really end up caring about in terms of the spectroscopy are the triplet pair states, the ones formed from 2 spin 1 particles, mainly because they tend to be the lowest in energy. And so in terms of affecting the dynamics of the systems, those will be the ones that, again, come and have the most relevance for determining the fate of the carriers as a function of time. So we get 3 possible net magnetizations, a singlet, 3 triplets, a set of quintets. Again, let's not worry about the counting number. And we're going to label those as our Biexciton states. And we're going to call them 1 TT for the singlet, 3 TT for the triplet, 5 TT for the quintet, and so on and so forth. So let's look at the relevant energy scales for each of these, the singlet state, the triplet state, the Biexciton, and these sublevels. So the excitons themselves, I'll pick one particular singlet fission molecule, pentacene, just to be consistent. So it has a singlet exciton of something, close to 2 volts, and a triplet energy slightly less than a volt. So it satisfies, again, our conservation of energy criteria. If you look at the binding energy, again, look at calculations that have been done on molecular solids, you tend to get answers in the order of 0.5 volt, very similar to our quantum dot. And also similar is the Biexciton binding energy, which is not like the quantum dots, again, depends a lot on context. Depends on what chromophores you're using, the exact arrangement of the chromophores relative to each other. But in calculations, people have come up with differences between twice the isolated triplet compared to the bound triplet of something like, 100-ish millivolts. Again, very similar to what we see in quantum dots, which is a point I'll come back to. But what about these sublevels? We talked about, or at least I told you, that spin is essential in determining the recombination. And so if we think about, we have these 3 states with different net magnetization, what is the splitting between them? Without spending too much time on the Hamiltonian for the triplet pair, the answer to the splitting depends on basically 2 different energy scales. One would be the interchromophore exchange coupling, and the other one would be the basically the zero field parameter of the individual chromophore. So we have a J term describing how strong the interactions are between two chromophores. We have the zero field splitting D parameter that is characteristic of the chromophore itself. And if in the normal case, the interchain interactions or the interchromophore interactions are weak, and our energy levels tend to be close to degenerate, and they split and mix for ways we don't have to describe in too much detail now. But let me just say that this is the normal case where we find in solids, where you have weak exchange coupling, you tend to mix states of different, same parity, but different net magnetization. So the quintets and the singlets will start to mix, so you won't have a pure, so spin won't be a good quantum number, sorry. But anyway, the point being is that these energy levels will be very close to each other. And it's again set by a zero field splitting parameter, which is on the order of 5 microelectron volts. So we have half a volt for the exciton, 100-ish millivolts for the Biexciton, and then for the MTT sublevels, we're on the order of just a few microelectron volts, so way, way less than KT. You can also get in the strong exchange coupling regime, probably too much discussion for right now, but if the interchain or interchromophore interactions are stronger than the D parameter, then the levels split and don't mix, and spin is a good quantum number. We can have pure singlet, triplet, and quintet states. And for the majority of our talk, this is the regime we'll be in, although we'll talk about how we get into this regime later if we have time. So I've told you that these spin sublevel splittings are on the order of, let's just say, a micro electron volt. And so those are so much smaller than KT, they really can't matter in terms of the dynamics. And certainly there'd be no way we could see consequences of those splittings in things like transient absorption spectroscopy, where we're looking at electronic transitions like this one. This is a triplet excited state absorption from bipentacene. I'll show you the structure in a minute. We can do experiments where we put one triplet on a pentacene or two triplets on a pentacene, and we can look at differences in the line shape for the triplet absorption. And you can see we have line widths on the order of 250 millivolts, way greater than, again, what we said our sublevel splitting was. And even more concerning, there's even no difference between one triplet and two triplets in terms of the spectra we get. So again, you would think those splittings are so small they can't do anything. Or again, there's no way to see that using purely optical means. So I'm going to try to convince you that, again, maybe it's not a surprise that the spin splittings really do matter. They matter for everything really in terms of the recombination dynamics, and that looking not at the spectra, but at the trajectory of the populations as a function of time, we can really see which of the states is being populated and which one is dominating the recombination. So, right. We're going to use molecular systems of the type like this, where we take two chromophores and we tether them together. The synthesis is all done by Luis Campos's group. We like these systems because they represent the fundamental unit of singlet fission. It's constrained, there's no diffusion. We can control, Luis can control proximity and by the type of coupling unit, and where we put the bond, we can control the connectivity. You can make them dimers or trimers or polymers. And what this has allowed us to do is tailor molecules to specifically isolate these different spin states. And what we can show is that we can observe all of these MTT states and actually see which states are good and bad for achieving long-lived triplet pairs. So I'm going to run through just one slide each on each of these states. So hopefully this doesn't take too long. The first point I want to make is that if coupling is strong between two chromophores, we form 1TT states that never dephase. And 1TT state recombination is extremely fast and parasitic to this idea that we want to have long-lived states. Oh, sorry, you have 5 minutes left. That was at 12:20. All right, 3 minutes. Right, I won't give you all the details, but if it take a chromophore like this, where the two chromophores are directly linked, if you compare the lifetime of the triplet pair in this dimer to the lifetime of the singlet in this monomer, the triplet pair actually shortens by a factor of 20, actually more than 20. So what we've actually done is created a triplet that decays faster than the singlet. So that's certainly not bad. We can modify, no, certainly not good, sorry. we can modify the structure of dimers slightly, and we can observe that TT lifetimes persist for tens or even hundreds of nanoseconds. But again, what we need to do to create extremely long-lived states is dephase 1TT. That is unambiguously true. Okay. What we also can see is that quintet states and things that look like uncoupled triplets emerge in our molecules. Even without diffusion, this is a similar to molecule to what I showed you before, except for we've just pulled the chromophores spatially apart. And this is with spin resonance, not with optical spectroscopy. What we can see is unambiguous signatures of a quintet state, and the quintet state over time will decay, and over time we can see the formation of something that looks like an individual triplet. And I'll give you a sense of the dynamics at the end. Again, spin conservation, these quintet lifetimes can be on the order of 100 microseconds. 1 microsecond, sorry, that's not supposed to be 100. We can see the 3TT state not directly by spin resonance nor optical spectroscopy, but indirectly through the recombination. 1TT has to decay by losing both triplets to conserve spin. The quintet state can't decay at all. It can just scatter and form, again, things that look like free triplets. But our 3TT state, our net triplet, has a recombination mechanism very similar to our Auger recombination in semiconductor quantum dots. And so what should effectively happen if the 3TT state is dominant is that over time, we will lose exactly 50% of our triplet population. And we showed this in a number of systems. This is the one I showed you before. We have quintets. I'm just showing you the normalized triplet population. Over time, we get to a 50% plateau. This is a polymer in a completely different structure. This backbone extends. This is a non-conjugated backbone, and we have these dangling single fission chromophores off. But oops, I put the dash in the wrong place, but the 50% line is here. Again, we get to the 50% plateau. We can change the connectivity. There's a nice theory paper showing how this works and get to our 50% plateau without even changing the proximity, just changing the bonding. And then we can see 50% plateaus in sort of custom design systems where we put energy gradients in to spatially separate the triplet pairs. So they start close to each other and then progress to a more spatially separated state. So all of our systems, 1 minute left, wrap up, show, again, the best systems where we have really long triplet pair lifetimes, they all show evidence that the 3TT is the dominant recombination channel. I'm done. I will wrap up with one statement that I feel is important to say. There's a lot of arguments about what is singlet fission. You can say singlet fission is the formation of free triplets from a singlet. This is unphysical. It ignores all the essential information about the Biexciton states that are essential to getting this. So you can say, okay, well, let's just talk about the net reaction of singlet fission, where we go from S1 to 1TT to T1, T plus T1. But this ignores all the details of the dynamics, and it assumes that conversion is irreversible. People tend to say that the formation of the triplet pair is not singlet fission, that fission means two, and this is not two. But as I tried to set up in the beginning, we harvest bound states all the time. That's not a problematic thing that we have a bound state. What's problematic is if the bound state is too strong to dissociate. You could say the triplets break by first diffusing apart. That's also not true. That helps, but it's not a strict requirement. So this idea of what singlet fission is kind of a wrong question to ask. Singlet fission is this really complex, reversible set of dynamics where we form bound Biexcitons and they dephase and rephase on time scales. Again, exactly equivalent to what was proposed by Merrifield in the 70s and shown by Bardeen and others in, you know, the subsequent decades. So it's really this dynamical process. And the question we should really be asking is, how do we optimize the formation of a state for harvesting? And in my personal opinion, the answer to that question depends on how we propose to harvest them. And so I think I'll just leave it at that and acknowledge mostly Luis's group and the students and postdocs who have worked collaboratively between us over the years. And so thank you again for the time. Sorry I had to rush at the end, but I guess we have a few minutes for questions.
Yeah, no, great, really nice work. And I will just jump into the first question, which is, what is the energy difference between the triplet and quintet state? And is it possible to directly create the quintet state? I guess I'm assuming optically.
Yeah. So the energy differences are on the microvolt micro EV. If we're talking about the triplet pair and the quintet triplet pair, they're micro electron volts. They're tiny. But yet they stay polarized. In the ESR language, I had to learn this because I'm an optics person, so polarization means the orientation of the electric field vector. And in electron spin resonance, it means you're in a sublevel preferentially. So again, we have these quintet, triplet, singlet sublevels. If you have more population one than the other, in spin resonance, that's a polarization. So these states stay polarized, even though we have thermal scales much bigger than the energy splitting. You cannot directly form the quintet. No one believes you can directly form the quintet, I think, because of, again, spin angular momentum considerations. There's no way to get from the singlet to the quintet, but there's ways to get from the net singlet to the net quintet via various mixing processes. So one way to do it is to bring the singlet and quintet close together. That's true when we have these diffusive processes where, as we pull them apart, the exchange coupling gets weak, and then they start to mix. Because again, the spin is no longer a good quantum number. You can also have spin orbit coupling that will mix them. There's also orientational effects that will start to mix them. So there's all sorts of ways to get from 1TT to the rest of them, but not a good way to get from S1 to quintet directly. I think I don't think there's anyone who would argue with that, although maybe there is.
I certainly won't. So there's a request to put the references slide back on, just which is to your benefit.
Yes.
And then from Suggy, there's a question: is there a good understanding about the contribution of electron phonon or vibronic coupling to the separation and binding of the triplet pairs? So how do vibrations couple? And we talked a lot about spin.
Yeah, right. So this is okay. So if this is where the disclaimer comes in. There's been lots of work done, again, by people in this audience on vibrational coupling to generate the pairs. So I don't think you're asking about that, but let me just say that's not in our work, that's other people's work, and they've shown how vibrational coherence helps generate triplet pairs coherently. It's not the only mechanism, but it's one. In our particular molecules, all the triplet pair generation is incoherent, but electron phonon coupling does matter for the decay, particularly the 1TT. Yeah, this is all non-radiative decay. It's a radiationless, very fast radiationless decay process back to the ground state. This paper isn't out yet, but the group of Nandini and Nath at Cornell has done some really nice theory showing how 1TT can efficiently couple to basically a hot ground state, a vibronically hot ground state. So basically, you've just taken and enhanced the non-radiative radiationless decay in this molecule. So for the 1TT, it's super important. When you can conserve spin to get back to the ground state, it's extremely important.
Okay. Now I'm just going to ask my question, or one question, which is you have some nice work where you show that, spatial separation helps improve the decoherence of the spin and the survival of the triplet pair. But what about just the environment? I mean, if you just put in a solvent, well, there's temperature, obviously, and then there's, say, solvent with some hyperfine nucleus. I mean, is that another strategy that could possibly work?
Yeah, so temperature we've done. Below 50K, there's actually no effects of temperature. There's again, it depends on the molecule. And some of the molecules, we see some initial, what you would call activation, and then below 50K, nothing. So the dephasing is temperature independent over a large range at low temperature, and not significantly reduced. Solvent, you can certainly start to think about putting heavy atoms around. There's been baby steps at this in the literature, including by us. You actually affect both the pair and the singlet triplet in terms of their lifetimes. So it's kind of hard to pick out, we're preferentially bothering one of the sublevels. It looks like we're just bothering everything. So we haven't found the right knob to turn to do some systematic control of that yet, but we're working on it. I think it's an important approach.
But if you just deuterate the crap out of everything.
Yeah, we tried with the deuteration. The easy ones to deuterate, I think, are on the TIPS groups, and it doesn't have an effect. I have to look up and see if we deuterated the backbone, but we did some preliminary results. We saw no change in the rates. But we didn't do every molecule. It was before we really understood everything, and so we tended to do the molecules where 1TT dominates, and so it's possible it's just the timescales aren't there. So it's probably worth revisiting.
Okay, yeah, I know it's a synthetic challenge to deuterate around the acene core. That is basically you have to rebuild the whole thing, I think. Okay, so are there any other questions?
Put my conclusion slide up.
Oh yeah, get the references back up so that everybody can.
I was going to do this one. This was my
Oh.
conclusion, but then I was trying to say people can read them. And again, I
Okay.
just feel like, oh, sorry.
No, you go ahead.
Oh no, my take-home message is just how dynamic this process is, and what the molecules allow us to do is freeze the dynamics at some particular stage. But everything I've shown in molecules, it certainly applies to solid-state systems, and people have shown that again, including your own group. So that just wanted to put that disclaimer into.
Okay. Okay. So with that, I think let's thank Matt again for a nice summary and a nice extensive summary of the literature too. And I think we'll move now to the final limit, which is Vannier excitons or Vannier type excitons. I don't know if Lorenz is going to say that they're truly Vannier excitons in inorganic systems. So now we got the nanoparticles. I think you might be muted.
Yeah, okay. Thank you, Chris, for having me on board of this meeting, also to Suggy. I want to talk about multiple excitons in two-dimensional cat selenide nanoplatelets. So that are systems. Let me see. Yeah. So we are going to look at nanoplatelets that are consisting of cat selenide. They are ultra thin, 1.4 nanometer. That corresponds to 4.5 cat selenide layers. And here you see TEM images. They have a length of about 34 nanometers and a width of about 10 nanometer. And they have a dielectric constant, a static dielectric constant of 10. But we have dissolved them in hexane. That's possible due to these oleic acid ligands on the surface. And that has a low dielectric permittivity of only 2. And what we wanted to know is if you photoexcite these nanoplatelets, do you really get excitons or do you get free charges? And in particular, what is the effect of the photoexcitation density? So if you fill up such a nanoplatelet by producing many excitons, by absorbing many photons in one nanoplatelet, do you get stable excitons that are sitting next to each other? Or do electrons not know anymore to which hole they belong, and do they spread out and move all over the place like the holes do? And you get a sort of metallic system, which is known as an electron hole plasma. Now, a little bit more about these nanoplatelets. We can dissolve them in hexane. They look yellow, and that's because their band gap is close to 2.4 eV. That is about 0.7 eV higher than for bulk cadmium selenide, and that is due to the quantum confinement. The bulk exciton Bohr radius is 5.4 nanometer. Our sheet thickness is only 1.4 nanometer, so you squeeze the excitons to be flat, and that gives rise to quantum confinement, and it gives rise to these sharp peaks like you have in quantum dots, and then there is a continuum here due to excitation to higher lying states. Now, how do we interpret these spectra? So we have this first peak, a second peak, and then continua. Now, in the bulk, you have a conduction band, and you have a heavy hole band and a light hole band. And now you can excite an electron from the heavy hole band and to a heavy hole exciton, and that gives rise to this first sharp peak. But you could also excite an electron from the light hole band, which is lying a little bit deeper, to produce an exciton, and that's giving this light hole exciton peak. And then there are continua where you directly excite an electron from the valence band to the conduction band, and you produce free charges. Now, we estimated the binding energy of an exciton, so that is the energy difference between the continuum, where you produce a hole in the high hole valence band and an electron in the conduction band, and this bound exciton level by doing some phenomenological fit. And then we found a value of 193 millielectron volts. So that is almost 8 times kT. So excitons really have a high binding energy. And that is much higher than the 4 times the bulk energy. So if you just reduce the dimension from 3D to 2D, then theoretically you expect a 4-fold enhancement of the exciton binding energy, but 4 times the bulk binding energy would be 60 millielectron volt, and we have more than 3 times higher exciton binding energy, and that we think is due to the low dielectric constant of the surrounding solvent, that's hexane, and the organic ligands. And from this exciton binding energy, using the two-dimensional hydrogen model, we can calculate the exciton bore radius, which then turns out to be 1.2 nanometers. So the diameter of the exciton is only 2.4 nanometer, which is much smaller than the about 6 nanometer exciton bore radius in 3 dimensions. So we get small, tiny excitons that are flat, confined in the vertical direction. Now, coming back to the research question, that was, if we excite such a nanoplatelet with many photons, what is then the effect of density? Do we get excitons all the time, or do we get free charges? And to investigate that, we used, first of all, the technique of optical pump and terahertz probe spectroscopy. Now, what's that? If you have a sample here, let's say a cuvette with these nanosheets, we produce a terahertz probe pulse that is like a single cycle of an oscillating electric field. The time duration of this cycle is about a picosecond. So we get 10 to the 12th hertz or terahertz frequencies in there. And that is a photon energy of about 4 millielectron volt. Now, if we don't photo-excite the sample, the terahertz just goes through the sample. But if we optically pump the cat selenide nanosheets, then we either produce free charges, excitons, or both. Now, if you have free charges, then the terahertz wave, the electric field wave, can sweep up the motion of the charges a little bit, and in that way transfer energy to the charges, and due to that, the amplitude of the electric field will reduce. In addition to that, if you have excitons, excitons enhance the refractive index or the dielectric constant of the material, and that causes a phase lag that reduces the velocity of propagation of the terahertz radiation, and we can also measure that phase lag. So we measure the reduction of the amplitude and the phase lag. And these two things are related to what's known as the real and the imaginary conductivity. So the conductivity of a material is the number density of charge carriers times the electronic charge times the sum of the real and I times the complex number, the imaginary mobility. Now, what are these? If you have an electric field oscillating like E0 cosinus omega t, then the velocity of charges can be in phase with this field, and that is the amplitude of that in-phase component of the velocity is the real mobility, but it can also be that it lags behind a little bit the motion of the charge due to scattering, and that is known as the imaginary component of the mobility. So that's the velocity out of phase with the field. And if you have excitons, then the oscillating electric field can induce a dipole moment. So we have a field E naught cosinus omega t, then you can induce a dipole moment which is proportional to this electric field, and the proportionality constant is known as the exciton polarizability. And that contributes to the imaginary component of the conductivity. So altogether, we get a real conductivity, which is something with the sum of the electron and the hole mobilities times the quantum yield, the number of charges divided by the number of charges in excitons. And we get an imaginary conductivity, which can have a contribution of charges due to backscattering of charges on phonons or defects or edges of the nanoplatelets, and an imaginary conductivity, which is proportional to the exciton polarizability and the quantum yield of excitons. So this is the density of excitons divided by the sum of the density of charges and excitons. Now, we photoexcited these nanoplatelets at 480 nanometer with a short 50 femtosecond pump laser pulse, and we measured the real and the imaginary conductivity due to charges and excitons. Now, this is the conductivity. In the upper panel, I show the real conductivity. In the lower panel, negative, the imaginary conductivity. Here we photoexcited the nanoplatelets with on average 6 photons. And then we see a small real conductivity and a small imaginary conductivity, which hardly decay, or in fact don't decay on the 150 picosecond timescale here, because the lifetime of excitons exceeds tens of nanoseconds. Now, if you now go to a higher photoexcitation density, so here we excited in the red curves 53 electrons in a nanosheet, so we make 53 photoexcitations. Then you see that the real conductivity hardly goes up. Well, it goes up maybe with a factor 3 or something, but the imaginary, the imaginary conductivity goes up much more. That is about, let's say, going here from a magnitude of 1 to about 10. So it's about an order of magnitude, proportional to the number of absorbed photons per nanosheet. So you see a completely different behavior or dependence of the real and the imaginary conductivity on the density of photoexcitations. Now, to get further insight into what's going on, we also did optical pump and optical probe spectroscopy. So we photoexcite the nanosheets in a cuvette, and then we come in with a probe pulse, which is resonant with the heavy Hall exciton. So if you produce an exciton, you get reduced absorption because you have already promoted one electron. There's one electron less to promote, and you can induce stimulated emission of the excited electron back to the Hall state. So that gives net bleach. It gives more probe light coming through the sample, and the amount of probe light coming through the sample that is proportional to the number of excitons that you have produced with the pump pulse. So if you now look at the signals of this heavy Hall bleach signal for values of the number of photoexcitations per nanosheet close to those in the terahertz conductivity measurements, then you can see here the decay of the transient optical absorption for 7 electron hole pairs per nanosheet, and here for 70, which is somewhat higher than the 53. And you see that the relative magnitude of the heavy Hall bleach of the optical signal, the optical response, follows that of the terahertz response, and also the decay kinetics are similar. So that suggests already qualitatively that we have excitons all the time, that they survive at high density, and that we don't get a transition to an electron hole plasma where you have uncorrelated electrons and holes moving through each other. But we wanted to establish that a little bit more, so we did for a larger number of absorbed photons per nanosheets our measurements, the terahertz conductivity measurements. We average between 6 and 10 picoseconds after the pump pulse, so to reduce a little bit the noise level. And then we get these results. The real conductivity is shown here. That is due to free charges, which increases a tiny little bit. But the imaginary conductivity, yeah, that's close to linear increase with the number of absorbed photons per sheet. The curves shown here are from a theoretical model that I'm going to explain in the following. But first of all, let's say from the Bohr radius, we get that the cat selenide nanosheet would be fully filled with excitons if we would have 60 excitons. Here there's a factor of pi missing, I see. So you would expect for 53 photons absorbed per nanosheet that you're close to a nanosheet completely filled with excitons, close to the 60 that would fit in the nanosheet. So you could expect a transition to an electron hole plasma. That's what usually happens in bulk materials. If the excitons are sitting on top of each other, they dissociate into free charges. So why don't we have, so you could expect that you had no excitons, that you had this transition to an electron hole plasma, but according to these terahertz conductivity measurements, we have excitons. And the excitons are apparently stable even at a high density when they are sitting, let's say, next to, in contact with each other. And now we started theoretically looking at the equilibrium between free charges and excitons. So you have an electron and a hole, they can recombine to form an exciton, and in turn there can be thermal dissociation of the exciton into free electrons and free holes. Now we work this out using statistical thermodynamics. The density of electrons in a two-dimensional material is something with the effective mass of electrons, and there's the chemical potential over kT of the electrons, a similar expression for the holes, and this is Fermi-Dirac statistics. Excitons behave like bosons, so there you get Bose-Einstein statistics, so you have a minus sign here instead of this plus sign, and you have here the exciton binding energy that is subtracted from the chemical potential of the excitons. And then there is conservation of particle density, so the number of electrons and number of holes are equal, and that is equal to the number of charges in the system, and then the number of absorbed photons is equal to the number of charges plus the number of excitons. And in equilibrium, the sum of the electron and hole chemical potentials should be equal to the chemical potential of the excitons. But we still, in these equations, need the exciton binding energy. That is not the 193 millielectron volt that I talked about earlier, because that was for a single exciton. And if you have many excitons close together, and in addition, if you have free charges, they start screening the Coulomb potential. So the exciton binding energy will depend on the density of photoexcitations, which determines the density of free charges. So the two-dimensional Schrödinger equation is now containing the kinetic energy of the electrons and the holes, plus a potential energy that is a screened Coulomb potential with a screening length depending on the density of charges. And that gives you the exciton binding energy as a function of the density of charges. So the idea is that an electron, a free electron, could, let's say, gather around, or electrons could gather around the hole and screen the interaction with the other electron in an exciton, or you could say the electron moves in between the electron and the hole in an exciton. Now, the screened potential we took in the zero momentum or long wavelength limit, that's given by this expression. Lambda is a screening length, and here there is a Bessel function and a Struve function and so on. That's from literature. We took that expression, and then we calculated the screening length given by this expression as a function of the density of charges. And then, interestingly, you start with, of course, when NQ goes to zero, a very long screening length, so there is no screening, and then screening length becomes shorter when the density of charges or the number of charges per nanosheet increases, and then interestingly at very high density it becomes constant, and that's different from 3D where the screening length really goes through zero. And this constant screening length at high density is due to the fact that even if you have a high density in a very thin two-dimensional material, there are always field lines going through the surrounding medium, which in this case is the hexane solvent with a low dielectric constant of only 2. So you never reduce to a zero screening length because you always have interaction via the solvent. And if you now calculate by solving the Schrödinger equation, the exciton binding energy as a function of the number of charges in a nanosheet, you see that for a very small number of charges, or let's say when you go to zero, you get this 193, and that's what we put in here in the relative dielectric constant. And then if you increase the number of electrons and holes in a nanosheet, you see that you end up at the saturation value of the exciton binding energy, which is minus 45 millielectron volts. So at high density for this two-dimensional system, we get a finite screening length. There is still a remaining finite Coulomb potential between the electron and holes. It becomes constant, and you get a constant exciton energy, which is exciton binding energy, which is not going to zero. So the exciton binding energy saturates even at high charge density at 45 millielectron volt, which is larger than KT, which is 25 millielectron volt. So it's close to twice the thermal energy. So the excitons can also be present at high density, and you get no electron hole plasma. Now, we calculated these curves to reproduce the real and imaginary conductivity as a function of the number of absorbed photons per nanosheet. So we have these expressions for the conductivity that I've shown you already. We calculated the 2D exciton polarizability for the ideal case of a hydrogenic model in 2D, but we use the exciton binding energy as a function of the number of free charges. So the exciton binding energy goes down now when we are at a larger number of free charges or a higher number of absorbed photons per nanosheet. Now, the only fitting parameters we had is the mobility of the charges within a nanosheet, and that we took as adjustable parameters to get these curves, these theoretical curves, and we found that the DC mobility of electrons and holes had to be 527 centimeters squared per volt second and 40 centimeters squared per volt second, and these fitted values are close to the bulk values. They can deviate a little bit because the band structure of a 2D material deviates from the band structure of a 3D material, so the effective mass can be a little bit different. Now, if you look now at the density of free charges and excitons as a function of the number of absorbed photons in a nanosheet, you see that in fact you have a very small, this is the number of free charges in a Bohr area, that's much smaller than the number of excitons. And if you use these numbers here, if you calculate back, then for 50 photoexcitations in a nanosheet, we on average have 0.3 free electron hole pairs per nanosheet. So every 3 nanosheets, there's a free electron hole pair. And if you have 5 photons in a nanosheet, it's about 1 in 10 free electron hole pairs in a nanosheet. And what you clearly see is that it increases sublinearly. If you go from 5 to 50, and you could say, okay, then I get 10 times as many free electron hole pairs, but it is less because of the bimolecular electron hole recombination that gives a bias towards the excitons. Now then, something about the quantum yield of Biexcitons, you could say, when I have so many excitons present, are they going to bind together and form a Biexciton like a hydrogen molecule? And now from experiments, we inferred Biexciton binding energy 45 millielectron volt, and we did theoretical calculations with all the statistical thermodynamics involved, and then we can see that at room temperature, in the range where we did our experiments, so that is the number of photons per Bohr radius here, or the number of photons per nanosheet, then at the highest density we have about 60% of Biexcitons. But if you would cool down the sample, then we would get to close to 100% Biexcitons. And we would like to do such measurements in the future, and we can distinguish between the single excitons and the Biexcitons, because the Biexcitons have a smaller polarizability than that of two excitons. So if two excitons bind together to form a Biexciton, the polarizability and as a consequence, the imaginary conductivity should go down. Now that's something for the future. So to conclude, we think that excitons are stable in cadmium selenide nanosheets, even at a high density where they start touching each other. And that is due to the saturation of the screening by charges at high density in a 2D system, surrounded by a low dielectric solvent. And that's good news for use of these nanosheets in lasers or LEDs that operate at a high density, because there you want stable excitons. And we think that at even a higher density, at some point you should get a crossover to an electron hole pair, electron hole plasma, because the excitons also start screening each other, and I did not take that into account. We only took into account so far the screening between the screening by charges, and so the screening between an electron and a hole in an exciton by free charges moving around, but excitons mutually also screen each other, because the dielectric constant is reduced when an exciton is surrounded by many other excitons. That's also future work. Now, I want to acknowledge people that did the work. It was still done before COVID. You can see we are still standing together. Lots of work has been done by PhD student Aditya Kulkarni, postdoc Miguel Faila, technician Jos Thieme. We got samples from Pieter Geirigat and Seger Hens from Belgium, and from Daniel van Makenburg and Bas Salzman in Utrecht. And we did the theory together with PhD student Francisco Garcia Flores, who is supervised by Henk Stoof from Utrecht. And the funding came from the Netherlands Organization for Scientific Research. And thanks very much for your attention.
Well, thank you, Lawrence, for that. It's pretty surprising results there. Let me jump to, well, the first question from our host. Is it possible to increase the thickness of the nanosheet and see the transition from 2D to 3D?
Yeah, that's an interesting question. You can make it a tiny bit thicker and thinner, but not much. I think they have gone to about 7 monolayers, but we haven't seen we haven't studied that yet. But that's indeed an obvious thing to do, make it thicker and thinner. And then you should go more to the 3D and the 2D case. So for thicker sheets, you would expect more charges.
Okay, and then here's another question that's sort of related to that. Again, how can you tune the experimental parameters? What kind of control do you have over the solvent dielectric, and can you use an ionic liquid?
Well, these organic ligands are non-polar. It's oleic acid with this aliphatic tail. So I'm afraid that an ionic liquid wouldn't work. It's an interesting idea to have something polar or ionic even to enhance the dielectric constant, because then, yeah, the dielectric contrast is reduced. But I don't know much about ionic liquids. I would say, due to the non-polar character of the ligands, it's probably not possible, but maybe I'm wrong.
Yeah, I don't know. I know that ionic liquids, sometimes they can have like a polar and non-polar part. You can dissolve a lot of stuff, it turns out, in ionic liquids, but I don't know that much about them either. Anyway, I had a question that was just, why Oh, actually, here's a question from Mark Wilson, so I'll jump to that one. Thanks for the interesting talk. Much has been said about the role of carrier trapping at the surface. How would these effects influence your observable? And can you give an upper limit on their probability? So
yeah, we have a publication on that, and we think that half of the nanoplatelets contain one defect. So let's say in half of the platelets, you would lose one exciton. And we studied that by a combination of terahertz spectroscopy, transient optical absorption spectroscopy, and photoluminescence. And we combined the decay kinetics in all these three experiments as a function of photoexcitation density. We puzzled a long time, and then we could only explain it by assuming that we have a fraction of platelets without defects, trapping excitons and charges, and a population of about 50% nanoplatelets with on the average one defect. Now, not on the average, with one defect.
So then would you say that the feature of these 2D platelets is that they're just way more surface defect free than the spherical nanoparticles that most people study?
Yes, yeah, that's the idea. And the photoluminescence quantum yield is also quite high in these nanoplatelets. Yeah.
Okay. So my question was basically, at low temperature, you have a very high concentration of biexcitons, but what stops the excitons from just making and making an exciton crystal even at very low temperature? And then
good question, interesting question, and maybe that happens. You get a sort of crystal. We only looked at biexcitons in the theory so far, and according to theory, you would get biexcitons. We haven't done calculations on tri-excitons and complexes of 4, 5 or more, or even crystal, and maybe that happens. Yeah,
that would be super remarkable, I guess. You'd have it'd be one giant molecule at that point. And then another question from the private chat is what happens to the photoluminescence as you create more and more excitons or biexcitons in the material?
Yeah, that the photoluminescence quantum yield goes down because you get more Auger recombination. So so there is a faster decay when you have multiple X. So the photoluminescence quantum yield goes down because there is a competing channel. The Auger recombination competes with the photoluminescence.
Okay, but do you see any? I'm just going to amplify on that question. Do you see any sort of signature shifting or change in line shape at the high exciton? Okay.
Right. In one of the papers, together with the people from Ghent, we looked at that. Yes, and you see in the photoluminescence a red shift because you form these multiple exciton complexes.
Okay. All right. Yeah, that's the classical signature, right? I think of biexciton formation. Okay. Those are my questions. I don't know if anyone has more questions either from the chat or just verbally if they want to chime in. But I'm not seeing it, so I think maybe we've exhausted the questions here.